want to define what we mean by resource partitioning. And intuitively, what resource partitioning means is that it's ways in which species are different in resource use. And so you might have a set of species, for example, the paramecium pair, that one of them ate bacteria and the other one ate yeast. And so they sort of partitioned the resource by eating different kinds of food. And of course, that can favor coexistence, as it did in the Gauss experiments with paramecium. And there are various ways in which species can differ in resource use. And these possible kinds of ways can be roughly divided into food type, space, and time. So food type, there's a bunch of possible ways to subdivide that. Might be different sizes of food. Might be different hardnesses of food, as in finches that crack seeds of different hardness. It might be taxon, as in the case of the paramecium, where you had some feeding on bacteria, and that's a different taxon from others feeding on yeast. And so, there are various ways in which this can be subdivided. Space, sometimes that's called habitat. You hear habitat all the time. So habitat means essentially it involves spatial characteristics, and for ecology or biology, the habitat characterizes where in space a species inhabits or lives, and there are various ways that you can describe its habitat, as we'll see, in many ways. But for now, I'm just going to distinguish a broad and a narrow spatial scale. And appropriately, the broad spatial scale is called macrohabitat, and the narrow spatial scale is called microhabitat. So an example of a broad spatial scale is vegetation over an island. So you might have desert versus rainforest, for example, as different types of vegetation. And an example of a narrow spatial scale or microhabitat is where they occur in a tree. So some of them might occur on the tops of trees or on really tips of branches, and other ones maybe on the tree trunk. And so there's various possible microspatial differences. And of course there are in-betweens between these two things, but those terms are commonly used. And then time, the third possible way in which resources can be divided, are daily activity time and seasonal time. So some species will be active the hottest part of the day, and others maybe will be active at dawn and dusk, and others will be active at night. And seasonal, some species are active in cold months and some in warm months. And all those things lead to the consumption of different resources or resource species, and are ways that species can partition resources. Now, the language of resource partitioning is the ecological niche. And this term comes up over and over and over again in so I made a diagram of this for your notes. It's a little hard to draw this. It's very hard to draw this, actually. This idea comes up over and over again in different guises with different definitions, and depending on what textbook you use or what course you take, you might get a different definition. So I'm only going to give you one definition of the ecological niche, which is the one that's going to be most useful for what will follow in this, under this topic head. And this sounds like a mouthful. It's a multidimensional utilization distribution. So what's a distribution? A distribution is just a frequency histogram. So here's the frequency, and we've had this already with respect to other types of things. So here's the frequency of some category, say prey size, just a percentage that occurs in, say, the diet of a particular species. And here are the prey size categories. So these are large prey and these are small prey. And here, the most abundant type of prey is intermediate sized prey. So all these little boxes should add up to 100% or 1.0 if you're using decimal frequencies. And that's all it is, it's a frequency histogram. So this thing is the ecological niche with respect to prey size. If only prey size were important in resource partitioning, then this would be a complete description of the ecological niche, and it would be one-dimensional. Now, this one is just to indicate that we often draw a smooth curve through the frequency histogram. because it's easier to draw that than it is to draw these little boxes. And so this curve, this bell-shaped curve, is roughly, and it doesn't have to be bell-shaped, but this one is, roughly drawing the curve, smooth curve, through the frequency histogram. So these two are equivalent. This is just a shorthand way of drawing that. Now it might be, in this case, that we don't have a one-dimensional niche, but we have a several-dimensional niche. And that's where this multi-dimensional comes into the picture. In this case, dimensions are represented here in a three-dimensional plot, and the back of this plot is the same as this, which is the frequency that's going up, the vertical thing that increases going up, the frequency versus the price size categories, which are out here. They're the same as those. And now we have this other face here, which is frequency versus perch height categories. And these are the perch height categories. So these might be millimeters prey size, and these might be, say, centimeters or meters in perch height. And together, they describe a multidimensional distribution, and its utilization, that's a fancy word for use, because what we're doing is doing one of these for a population of a species. That is to say, all the individuals in one place. If you combine their diets and where they feed, you're going to get this kind of a distribution, depending on whether it's this one dimension or two dimensions. And so all of these little boxes here give you the joint categories, joint between prey size and perch height. So this one, let's take this one. This one says they take prey between 6 and 7 millimeters. This is hard to read exactly. And they perch between 2 and 3 feet. But you can see roughly how that would go. And now you can continue to do this for 3 or more dimensions. We're up to 2, and we've already run out of 3-dimensional space because our third axis is frequency. But we could do an array, just like a computer array, where we have all the possible joint combinations of, say, perch height, prey size, and maybe perch diameter, the diameter of the twigs where they take their food, or it could be something else. And we can go on like that indefinitely, and there's nothing to stop us from writing down complicated arrays. It's just that we can't picture them very well. But in theory, we can have this be multidimensional. As this one is, it's only 2 dimensions. Utilization, it tells you the frequency of use for the species, in this case, proportion in the diet of all the individuals of the species combined in that one place that we're looking at it at. And in this case, in addition to that, the heights at which all the resources were taken for that particular species. And then distribution, that's what a distribution is. It's just a frequency histogram. That's a statistical distribution. So that's my definition of the niche. Questions about that? Yes. Question, please. Yes. I see a hand coming out over there. I'll come out. What?
Can you describe utilization again?
Yeah, utilization is use. So let's look at this one. Let's look at this one. How do we get this? So what we do is we go out and we note for a bunch of individuals of a species in some place what its prey sizes were that it was eating. So, and then we might have 10 individuals or 100, and then we combine those prey sizes to get a representation of what the population eats. Okay, and the same with height would be, you do observations of heights of individuals and then combine them. So one of the ways to get prey sizes is to do stomach content analyses. So you might have, say, 50 individual fish, and you open them up and you see what the sizes of all the foods were that the 50 individuals had, and then you make a frequency distribution of that. Okay? So I think instead of showing examples from real organisms now, that we ought to have some music. And lucky you, we've got a Gary Grossman on tap. Yeah, I heard somebody say yes. We're getting fans here. it's okay to stand up and cheer and all exist 8 different foods. And this whole idea of coexistence being possible when species mainly take different resources has been enshrined in something called the Gauss principle. And it's basically, in my terminology, I've watered it down a little bit. Species cannot coexist if they use resources too similarly. So the idea is that if species do use resources too similarly, then one will eliminate the other. It'll be competitively superior according to cases 1, 2, or 4. And if not, then we have case 3. And we'll see that formalized in a bit. But people then ran out when Gauss did these experiments and a little bit before, and went into the field and asked how do species actually differ in their resource use, and they argued that that gives them the means to coexist. I'm just going to run through some examples. Christmas Island is in the Indian Ocean, and we have 5 terns on Christmas Island. It actually says terms. I never noticed that before. Anyway, terns on Christmas Island, and there were 2 ways. Well, there was one way in which these terns differed, and that is essentially a one-dimensional niche. And so here we have the frequency histograms, just as we have on the niche diagram that was in the previous slide. And we're looking at 2 types of prey. We're looking at the length of the fish food, and then they also eat squid, so we're looking at the size of the squids. And here we have these species arranged according to their size, with the bigger billed species at the top and the less hefty billed species at the bottom. And we're seeing that, in fact, that is reflected in the diet or the food size. And this food size is, the single dimension. And to respond to that question again, so how do you get these histograms? What you do is you go out and you note what a whole bunch of terns are eating, or maybe bringing to the nest or whatever, and then you bring to, in this case, not so much a nest, but to young birds that are walking around. And then you make this histogram, giving you the fraction of the total diet of the tern population on Christmas Island that consists of the different food sizes. So that's food size as a significant dimension. Now, the second one is microhabitat, and this is a famous case of 5 warblers. These are eastern warblers. We have a couple of warblers out here, but there are huge numbers of species of warblers in the east. The ovenbird was a warbler, but these are all more arboreal. And they partitioned by microhabitat, and a famous ecologist named MacArthur did this for his thesis. And what this shows is for these 5 species of warblers, where in the tree they most commonly feed. And you can see that some of them feed low, and some of them are high, and some of them are in outer parts of the tree, and some of them are inner parts of the tree. So where in the tree they feed is an example. It's not the only possibility, but it's an example of a kind of microhabitat. Next slide was done by Kathy Toft, who was a professor here and tragically died very young. But these are Dendrobates poison arrow frogs. We saw one of them that was aposematic in our anti-predator lecture. And it turns out there's a whole bunch of species of them in the Amazonian tropics, and here are 3 of them. And these are all essentially poison arrow type frogs. They're not all as aposematically colored as the one that I showed you before. And these differ in terms of their food sizes, as do the terns, but also the food taxon. And some of the frogs are specialized to feed on ants, for example. Okay. The 4th example is Conus gastropods. Okay, here we go. Conus studied by Kohn. Predestined. Any of you have last names that are animal names or occupations? Don't be shy. What is it? Hat maker? Oh, well, I think you were born too late. But maybe not. Maybe hats will get back into fashion. Anybody else?
Car.
Car? And does your father sell used cars?
No.
No. What? land and water?
Yeah, it's in Spanish though.
Oh, okay. I don't know what to say about that. Have your family members been in jail? Well, you better watch out. Drive carefully. They put you in jail for drunken driving these days, right? So, not that you would ever do that, of course. Okay, so Conus gastropods. They specialize in taxon, and amazingly, these things will catch. They're essentially immobile, but they have this poison barb called radula. And when you see a live conus shell, if you're beachcombing, especially in the Pacific, you don't want to pick one up at all. I mean, unless you're sure there's nothing in there, do not touch that thing, because the radula comes right out and will poison you, and it could even kill you. But anyway, it'll be very nasty for you for a while. And the way they catch prey is they just sort of sit there, they're immobile, and when something gets close enough, like this polychaete worm, out comes the radula and immobilizes it, and then it gets gobbled up into the digestive system of this conus organism. And believe it or not, they can even catch fish this way. Well, you know, the fish must just sort of snarf around here, and maybe they want to eat little bits of algae or scuzz or something like that, and then all of a sudden, out comes the radula, and the fish is caught. So there's some of them even specialize on that. And so the Conus gastropods specialize in terms of food taxon. So no discussion would be complete of this sort without anolis lizards, as you're beginning to find out. And here's a study of anolis lizards in Puerto Rico. And we're going to be dealing here with two types of habitat, macro and micro habitat. And we see that, and we'll also talk about food size last. So there are going to be three types of macro habitat. Remember, that's like vegetation zone. And one of them is wet forest. And then the micro habitats within the wet forest are places in the vegetation where different species occur. So here's species 1, 2, 3. And these species occur respectively in grass bush situations. So they occur in low shrubbery in the understory, or trunk ground. So they occur on fairly low trunks and facing toward the ground so that they can come to the ground to eat prey, or trunk crown. So they'll be up here in the crown of the vegetation, and they will be eating their prey up in the canopy, essentially, the canopy of trees. So in the wet forest, we have three species of different microhabitats. So here's macrohabitat, and then microhabitat goes across here, and we have these three species that you're seeing in front of you. So the next one, we'll go to intermediate forest. Now we're going to the drier areas of Puerto Rico. And the intermediate forest looks like this. You know, it's not lush as lush, it's sort of broken up. Looks a little like some of the forests around here. So the rainfall is substantially down, but it's not quite desert. And we have three more species that occur. These are different from the other three species, even though they look alike to some extent. There's the grass bush, the trunk ground, and the trunk crown. And we can see those here denoted by the X's. So all three of the microhabitats are represented here in this intermediate forest. And remember that, well, this looks a lot like the previous one. This one looks very much like the previous one. These don't, remember the previous one was green. But what's interesting is that this is a male and female of this intermediate trunk crown species, and that's the female of the previous one, the one that was in the wet forest. So the male is the one that was that bright green color, and this female is much like the intermediate, both sexes that are in the intermediate forest. And notice how camouflaged that thing would be. It's even got little specks of what look like moss growing on it, but it wouldn't be moss. And this is a pair that's copulating, the male slightly larger than the female. And then we get to the dry area, the really dry area, where everything really dries out. And we end up with only two of the three microhabitat specialists. And we no longer really have a forest, it's just a bunch of shrubs, and including cactus. So here's the grass bush, now it's on a cactus. A cactus is the bush. And then here's the trunk ground. And they look pretty much like they did in the other thing, but there's no canopy. so that the species that was the trunk crown in these other two vegetation types, macrohabitats, that species is gone. So we have so far now a total of 8 species. But there's another one yet, and that's where we get into food size. And these species are pretty much the same size between microhabitats. But now we have something called a giant anole, which is much larger than the other ones. This is actually a baby giant, but look at the size of its tail, it's amazing. And it occurs, the giant, occurs in a, it's here. So the giant occurs in the wet and intermediate areas where you have substantial trees. And it's mainly in the trunk crown rather than the trunk ground, but it can be to some extent in the trunk ground. And it specializes on much larger food sizes. So it'll eat things like bird eggs and other lizards and all kinds of things like that, big fruits. So those are just examples of all of this from the animal world. And we can go to the plant world and find another example. Now, in the case of plants, some people have argued that plants all roughly require the same thing. They require different nutrients like nitrogen and phosphorus and so on. They require water. And so, you don't really have to look at resource partitioning in plants. So here are 5 kinds of plants in the tundra. And for example, all plants need nitrogen. So how could there be resource partitioning? Well, it turns out it was rather recently discovered that nitrogen is not a single resource, but it comes in different forms. It comes in ammonium, nitrate, and free amino acids. And surprisingly, different plants in this Arctic tundra specialize on different forms of nitrogen. So they're chemical specialists. They all require nitrogen, but they get their nitrogen in different chemical formats. And they also show differences in the depth of nutrient uptake, that is the root, differences in how far the roots go into the soil or whatever it is there, and the seasonal timing, that is whether some of them are earlier than others. And the tundra is fairly short, so they are squeezed into a fairly short season, but still there are some temporal differences, some seasonal differences, as we discussed when we talked about the ways in which resources can be classified. And you can predict from knowing their nitrogen requirements, the chemical nitrogen format requirements, and how they get the depth of the resources that will be available and the seasonal time, which species will be where in the tundra. So it's not as dramatic as some of the animal examples, but it certainly occurs. Okay. Now, people have then said, well, okay, fine, you have all this resource partitioning, but how do you know that this resource partitioning is not just due to chance? That is to say, maybe species evolved without respect to one another, contradicting the Gary Grossman thing. They don't have to shift with respect to one another, and they just happen to end up doing different things. How do we know it's more blatant than that? How do we know it's more stylized, more dramatic than just sort of coincidental differences that didn't have anything to do with competition? And there's 2 ways to discover that. One is to look at limiting similarity models, and another way is to look at statistical models where you try to generate a distribution of differences between species that would be expected were the species not affecting one another in terms of competition. And that's a big mouthful, so you don't know what I said there, but you will shortly. But have a look at this first part first. So this first part is looking at limiting similarity. The handout is now 7. And we want to look at the ecological niches. So we're going to look at the utilizations. Remember we said the utilizations can be represented sometimes by bell-shaped smooth curves? So just think of these as bell-shaped curves. You can think of this as food size, or it might be perch height or something else. And so we have some continuous dimension, and we're going to look at 2 species, and we want to define limiting similarity as that degree of similarity that just allows coexistence Any greater similarity would result in one of the species becoming extinct. So the shaded area here represents overlap between the niches of species A and species B. So if this is food size, A takes smaller food than B. Right? And here's the overlap. So this is where both of the species are taking food. So they're jointly interfering with one another. And it might be that these species are more similar in their food size. The more similar they are, the more you can squish these two niches together, and the greater the area of overlap. So, or they might be very dissimilar, as in the third panel, in which case there's almost no overlap at all. And these are almost perfectly separated. So here's the intermediate case. Here's a lot of overlap. Here's a little bit of overlap. And what we've tried to show here is that there's some amount of overlap at which the species will just coexist, such that any greater overlap, like down here, one of the species will exterminate the other, as in the models. Any less than the limiting similarity overlap, they're still okay. They're even more different. So you can imagine species starting out somewhere, and when they're exactly at this point, they're exactly at the point at which similarity cannot be any greater. And it's sort of like similarity in the limit, limiting similarity. If a similarity gets any more, then they're too similar. And Gauss's principle comes in, and the models come in. And now the shaded area can be visualized as being related to the alpha of the Lotka-Volterra model. The bigger the shaded area, the bigger the alpha. So these guys, which are not coexisting, have great big alphas. And they're either going to be case 1, 2, or 4. These guys have small alphas, and they're going to be case 3. And limiting similarity is measured in units of D over W, where D is the distance between the peaks of these niches, and W is just the standard deviation. So, you know, if this is a statistical distribution, you can measure the mean, which is here, and the variance. And the variance isn't diagrammable this way, but if you take the square root of the variance, you get the standard deviation. And we're calling that W for niche width. And so the distance is the distance between the two averages or means, and W is the standard deviation, which is roughly from the midpoint here to the inflection point of that curve. And so D over W tells you how similar the species are. Now, all of these niches have similar W's. And here the D is intermediate, here the D is great, and here the D is small. So D over W is least for this, which is good. D over W is most for that, which is bad, and intermediate for that, which is just on the edge of coexistence. So we'll come back to that, obviously, but anyway, that's